Okay, in this segment we're going to be considering different approaches to analyzing something called a series parallel resistive network. So I suppose the first thing to do is to try to explain what a series parallel resistive network is. So here's an example of a simple series parallel resistive network. We have an R1, an R2, R3, and R4. The basic idea is that if we can take a network like this and through a succession of series or parallel equivalent circuit transformations we can collapse it into a single equivalent resistance, then it's a series parallel network. And so, for instance, we can recognize that R3 and R4 are connected in series. We can draw a box around those, and we could say that this is equivalent to R1, R2, and we replace what we've put here in this dashed line here with a single equivalent resistor whose value is R3 plus R4, the series combination of R3 and R4. And then we can recognize that, these two resistors, R2 and this equivalent resistor that we just got, are something we could collapse into a single equivalent resistor because they're two resistors in parallel. So we can draw our little dashed line around that, and we could say that this is equivalent to a resistor R1 in series with a single resistor whose value is given by R2 parallel R3 plus R4. And now, of course, we've got two resistors in series, and we could simply draw a box or a dashed line around those two and collapse those into a single equivalent resistor whose value is R1 plus R2 parallel R3 plus R4. So the basic idea is that we can, through a succession of, or a series of series and parallel equivalent circuit reductions, we can collapse the entire network into a single equivalent resistance whose value is given by some expression involving series and parallel combinations of the resistors in the original network. And of course, when you're first starting out, it might be helpful to draw a series of pictures like this that explicitly shows what we're doing as we go through this sort of collapse. But you can also read this expression here directly off the topology of the original network. So if I look here, I see R1 in series with something. I have to go through R1 to get to the other side to get to that other something. And so I can write R1 plus, because plus is how resistors combine in series. And then I see a branch point. So I have R2 in parallel with something else. So I can write R2 parallel. And then I see in this branch R3 in series with R4. So I can write R3 plus R4. And so instead of going through this sequence of pictures, I can actually, with a little bit of practice, arrive immediately at writing down this expression. And so hopefully, with a little bit of practice and with a little bit of care, you can get to that point without too much trouble. But this is the kind of network that we're going to be considering at the beginning. So this specific network is called a ladder network for fairly obvious reasons, because if you turn it on its side, it looks like a ladder. Especially if we draw sort of the output voltage as being sort of over here with the two little extensions. It looks very much like a ladder, where these R2 and R4 are the rungs of the ladder. And and so we're going to be considering this little 4 resistor ladder network, not because this is such a great useful circuit, but because it's a simple enough circuit where we can consider different approaches to solving the problem and illustrate some things about solution methods. Okay? So in particular, what we're going to be concerned with is trying to find out if we had, let's say, a voltage source connected to the left-hand side of this 4-resistor network. So this is Vn, R1, R2, R3, and R4. We're going to be interested in what is the output voltage here across R4 as a function of Vn. Okay, we're going to consider 3 different ways of solving this problem. The first approach that we're going to use on this problem is to apply a general method called nodal analysis. And nodal analysis is a generally applicable method of analyzing any linear network, and it's very powerful, and it's very good for doing things like proving theorems that hold in general about general networks. It's very good if you're writing a circuit simulator like SPICE that's going to systematically solve the circuit equations that you feed in to it. But it's actually quite a lousy method for human beings to use who are interested in gaining some insight into how a circuit works. But if you like, it's a method of last resort for human beings, I would say. But it's important that you kind of understand the general idea. And the basic steps are to, first of all, pick a reference node. And that is going to serve as the zero of potential. And this is what we often do when we think about measuring things all relative to, let's say, the ground rail. And that node is sometimes called the datum. And we denote it usually by attaching a little ground symbol to that node. And then we define node voltages which are the voltages on all of the other nodes in the circuit relative to the datum. So in this case, there are 3 other nodes in the circuit. There's this node here, which is Vn. And it's not really an unknown voltage because we actually have a voltage source that's defining that to be Vn. So that's not really going to be an unknown voltage for us. These node voltages are basically the unknowns in our system. And so this one really doesn't qualify as an unknown. So we're going to have 2 node voltages, V sub A and V sub B. And it so happens that V sub B is precisely the voltage that we're interested in solving for, V out. So by this choice of the datum, we automatically have this node voltage known because Vn is given relative to that, and V out is directly one of the unknowns that we would be solving for. In more general cases, when we haven't got such a fortunate choice for the datum, or we haven't made such a fortunate choice for the datum, we may have to solve for the node voltages and then express the thing we're interested in finding in terms of some linear combination of the 2 node voltages or the n node voltages that we're solving for. So the third step is write write a KCL equation for each node. That's not the datum. And express the currents in terms of the node voltages. For put it in a matrix and solve. Okay, we're gonna do that for this. We have here we could define some currents. We have I1, I2, I3, and I4. And we could say KCL at VA tells us, well, given the way that we've set up these currents, it tells us that the sum of the currents flowing in, I1, is equal to the sum of the currents flowing out, which is I2 plus I3. Okay, so I1 we can express as Vn minus Va, the voltage across R1, divided by R1, and that's equal to I2, which is Va, minus 0, which is our datum, divided by R2, plus Va minus Vb over R3, and this is I3. Okay, so that's our first equation. We write a KCL equation for node Vb. Well, this one is simpler. It's just I3 is equal to I4, and we can write I3 as Va minus Vb over R3 is equal to Vb minus 0 over R4, and this is I4. This is I3. And typically what we'll do is we'll put all the unknown voltages on the left-hand side and all the sources on the right-hand side. So if we transpose all of these things and collect everything up, our two equations would be, let's see, up here for the first equation we've got a 1 over R1 times Va on the right hand side. We have a 1 over R2 and a 1 over R3. And then we have a minus 1 over R3 times Vb. And that's going to be equal to Vn over R1 on the left-hand side. That's the first equation. The second equation, for VA, we're going to have a, let's put everything on this side. So we're going to have a minus 1 over R3 VA, and then we've got a two terms involving VB. We're going to have a plus 1 over R3. We've moved that to this side. Plus 1 over R4 VB, and that's going to be equal to 0 since that's what's left over here. And that's 0 amps because this is a V over R kind of equation. And these are currents because they're KCL equations. And so we can write this in a matrix form by just taking VA, VB as a vector kind of out, and we wind up with something like 1 over R3, or rather 1 over R1 plus 1 over R2 plus 1 over R3 minus 1 over R3 minus 1 over R3, 1 over R3 plus 1 over R4 times VA VB, and that's equal to Vn over R1, 0. And so this is our matrix system of equations that we need to solve. You can use whatever solution method you find expedient, Gaussian elimination, Gauss-Jordan elimination. In this case, since we're interested in just solving for VB, we could use something called Cramer's rule, which you may not have ever heard of before. But Cramer's rule is a way of expressing, a way of writing down the solution for one variable in a matrix system like this in terms of a ratio of determinants, and V out is just VB, and that would be given by the determinant in the denominator is going to be the determinant of this matrix here, 1 over R1 plus 1 over R2 plus 1 over R3 minus 1 over R3 minus 1 over R3, 1 over R3 plus 1 over R4. And then up in the numerator, what we do is we take the column of this matrix here and replace, or we take this matrix here and we replace the column of the variable that corresponding to the variable that we want to solve for with the column vector on the right hand side here. The details really don't matter, but we would have 1 over R1 plus 1 over R2 plus 1 over R3 minus 1 over R3, 0, and Vn over R1. And of course, you may or may not have ever seen how to write down or evaluate a 2 by 2 determinant. You basically multiply the main diagonal and then subtract the multiplication of the off diagonal or the anti-diagonal term, and when you do that, you simplify, what you get out is Vn, or rather V out, is equal to Vn times, in the numerator we get R2, R4, in the denominator we get R1, R2, plus R1, R3, plus R1, R4, plus R2, R3, plus R2, R4. And this answer is correct. And I don't really care precisely what it is. I just want to note the character of it. So what you get when you apply this type of analysis strategy in general is a rational function here, a ratio of sums of products of the components in the circuit. And it's all kind of mixed together, right? These sums of products of the element values are not arranged in nice sort of series or parallel combinations with each other. It's just all kind of multiplied out. And if you put this into some sort of symbolic math package like Wolfram Alpha or Mathematica or Maple or something like that, there's some canonical form that some mathematician has decided is useful or is aesthetically pleasing or something like that, and that's what comes out. And that's not going to be very useful for us if we want to understand something about how the circuit is working. That would be at least my claim. And this type of analysis always results in this type of answer. And from a design point of view, where we might like to know, hey, what element should I tweak in what direction to get the gain of the system or whatever, which is what this thing represents. How much does V out change as a function of V in? How much does that? How much does each component affect the result? You just have no way of knowing that. And I would also argue that this type of analysis really kind of puts a layer of stuff between us and what's actually going on in the circuit. We basically throw it all into a matrix, write down a matrix system of equations, and then we turn some crank in some algorithm someplace, and we don't get the benefit of actually having to stay close to the circuit and to think about what's going on in the circuit. And so, as a general solution strategy, my recommendation with respect to nodal analysis is that is a method of last resort, and it is something that is good for computers to do, but not something that's so good for human circuit designers to do. So what would I recommend instead? I'm going to consider two different approaches to the circuit and to the same problem, and I would say that they are both better than nodal analysis for humans, although they do require some practice and some care and some insight. But what I think they do buy us is they buy us a way of actually thinking through what's going on in the circuit, and it gives us an answer that is interpretable in terms of how the circuit is actually working. Okay, so it's the same problem we're interested in solving. And the first method that we'll consider is what I'm going to call a succession of voltage dividers. So here's the idea. If I knew what this voltage was here, V2, if that were my input voltage, let's say, I could write down V out using the voltage divider rule. Right? So V out would just be given by V2 times R4 over R3 plus R4. However, V2 is not my input. It's actually an intermediate node. But if I think about taking these three resistors, R2, R3, and R4, and if I were to collapse them all into a single equivalent resistor, then the voltage here, V2, what I've called V2 here, would actually be something that I could write down as a two-way voltage divider from V in. And so I can get V2 by collapsing these resistors into a single equivalent resistor and writing down V2 using a one voltage divider ratio. And then I could imagine re-expanding this out once I know V2 and write down V out as V2 times that second voltage divider. Okay? And so I can do that. I could write that out in a succession of steps if I wanted to, but with a little bit of practice, you can actually do this all in one step, quote, by inspection, as we might say. And that's not to mystify you. That's basically just to say that it's something with a little bit of practice you can actually do without having to do a bunch of intermediate steps and a bunch of algebra, which of course reduces the probability of actually making an algebraic error, which is really nice. So we can write down V out as V in times, well, let me do this collapse here. So this set of three resistors I can collapse into a single equivalent resistor whose value is R2 in parallel with R3 plus R4. let's see there. And that's kind of in the canonical R2 position in our two-way voltage divider. And so the voltage divider ratio is R2 here, the canonical R2 divided by the canonical R1 plus the canonical R2. And this would be, if you like, V2 divided by Vn. So what I've labeled here V2. This is a voltage divider ratio, and multiplying this ratio times Vn gives me V2. And then, once I know V2, I can multiply that by this second voltage divider ratio, which is going to be R4 divided by R3 plus R4. And that is V out over V2. So if you like, the product of V in times V2 over Vn gives me V2, and the product of V2 times V out over V2 gives me V out. And so this expression, in contrast to the one that I erased from up here, is not just simply the sum of products of some circuit elements divided by the sums of products of some circuit elements, but these circuit elements are grouped in natural groupings that correspond to the structure of the network. They're interpretable as things like voltage divider ratios. I can say, because I know something about, like, if I have two disparate types of resistors connected in series, I know that the series combination is dominated by whichever one is larger, if one of them is much larger than the other one. Or if I know that there's this parallel combination here, if I know that R2 is much smaller than one of these two resistors, then I can make some approximations based on the notion that the parallel combination is dominated by the smaller of the two resistors, or the series combination is dominated by the larger of two resistors. So in these sort of natural groupings that just emerge out of this approach, you can do things like make approximations in ways that would be very difficult to do in the symbol soup, which is the result of doing something like nodal analysis. So that's approach one. There's not much to it. You just write it down. The second approach, which we might take to this particular circuit, we could call Ohm's law, current divider, Ohm's law. So these are more ad hoc circuit solution methodologies, and they do require a little bit of care, a little bit of practice. But the basic idea here is that if I knew the current flowing through this resistor R4, let me call it I4, if I knew that current, I could write V out as basically I times R as through Ohm's law. Well, how would I know what that current is? Well, if I knew how much current was flowing out of R1 into this node here, some of it would go this way, and some of it would go this way. And the amount that goes this way is I4. And so I could write that down, knowing IN, as IN times a current divider ratio to get I4. Well, how could I get IN? Well, I can get IN by taking this entire network and collapsing it into a single equivalent resistance, and using Ohm's law to say that IN is just Vn divided by that equivalent resistance. And so the way that might go is I could write V out is equal to, start out with IN, Vn over the equivalent resistance of this whole network collapsed into a single thing, and we talked about that, so we can write that down by just reading it off the network. We see R1 in series with, which is R1 plus, R2 in parallel with R3 plus R4. And this is just IN. Well, now we know what IN is. We need to basically find I4 by using a two-way current divider. Okay, we had three different ways we could write down this two-way current divider. One way in terms of the branch resistances was the parallel combination of the branch resistances divided by the branch resistance of the branch whose current we want to know. And so to get I4, we can write down IN times the current divider ratio, which is the parallel combination of R2 parallel R3 plus R4. Divided by the resistance of the branch whose current we want to know, which is just R3 plus R4. So this is a current divider, I4 over IN. So the product of these two things gives us I4, and knowing I4, we can get V out by the IR drop across R4. So I4 times R4 gives us V out. And this is the answer. And it so happens that by just sort of shifting things over here, it's very readily apparent that these two alternative ways of arriving at the answer are exactly the same, right? So if I move the R4 off here and I move the numerator in this voltage divider ratio over here and group it with the R3 plus R4, I get my current divider ratio. If I move the Vin over to the numerator of what's left here of this voltage divider ratio, well, I just get my original Ohm's law input current. So it's readily transparent that these two are equivalent to each other. They're exactly equal and of the same form, but they have a slightly different interpretation based on the way that we thought about the circuit. If we had picked a slightly different way of writing the current divider ratio here, it wouldn't be quite so transparent, and we might have to do something like expand something out or cancel something, like maybe expand this R2 parallel R3 plus R4 out in the product over the sum and cancel an R3 plus R4 out or something like that to get the way that the current divider ratio would have been expressed. Like if we had expressed it as the resistance of the branch whose current we don't care about divided by the sum of all the branch resistances, we'd have something like that. We'd have a little bit of algebraic work to do to show that these are equivalent. But these approaches are ones that where we can write the answer that we care about by inspection, and as a byproduct of the process of doing that carefully, we've spent a lot of time thinking about how the circuit is working, thinking about how the currents move through the circuit, how they divide, and how they conspire to produce the thing that we are interested in knowing in the circuit. And that thought process, getting to know the circuit, is something that pays dividends in understanding how the circuit works and how, in some cases, we might change it to create a new circuit, or gives us some information, some extra information in terms of these groupings about the relative effects of changing various circuit element values in determining the overall output in such a way that nodal analysis would never do. Okay, so I would commend to you considering this style of circuit analysis as a promising approach for working with circuits that you care about designing. So I don't really so much care what the voltage is here as a function of these 4 resistors. Like I said, this is an example of a circuit that is primarily just for pedagogical purposes and not necessarily for any particular circuit function that it's capable of doing. But hopefully this has at least suggested to you that that this approach is in some ways better than nodal analysis. I should say that there is a by inspection way of writing down the matrix system of equations that you have to solve in nodal analysis, and people seem to like that that fact. But from my point of view, it's always better to write the answer down by inspection to the problem that you need to solve, rather than the system of equations that you then have to solve by turning some crank. So anyway, that's it for this segment. We'll see you next time.